Okay, folks, here we are in week 15, the final week of Business 2220. Can you believe it? Did you think we'd ever reach the end? Well, here we are, the last week. And this week we're doing linear regression. Can we plot the data? Can we apply a ruler and make some predictions using the trend line that results? Well, that's the question we're going to ask and answer in chapter 13. I'm going to do a series of not one, not two, not three, but four related problems in this chapter. 13, 9, 16, 22, I believe it is. I didn't put it on the title up there, and 33. Give you an idea how this all works. Okay, what we're looking at here is the relationship, perhaps, we don't know yet, between home size and sales price. Can we expect there to be a relationship? You and I would probably suspect that the larger the house, the higher the price, but we're going to be a little more scientific about it and come up with some parameters so we can predict the price of a house. Now these data I should say, come from a 1986 survey, so it's a little outdated, but the concepts are the same. Don't go out and apply for a mortgage based on these numbers, obviously. Now the book gives us on page 513, or 514 rather, the min tab output, or one of them. At any rate, we're not going to use that. We're going to do our own, right? Right. So I brought in the data here from the CD, and you notice I've rearranged it slightly. I put the X, the dependent variable, in the first column, the left-hand column, and the independent variable in the X in the first column, and the Y value, the dependent variable, in the second column. That makes things a lot easier for Excel to interpret. So I'm going to select, I'm going to reverse the order of these, X and Y. Now I'm going to select this data, these data, and I'm going to insert a scatter diagram. And we'll do the one without any lines. We'll add a line here in a minute. Okay, there's our chart. Now, I'm going to do a couple of things. First thing I'm going to do is get rid of this dumb thing. And I'm going to click on the data points. You can see they become selected now. And I'm going to right-click. If you're on a Mac, it would be a control-click. And I'm going to add a trend line, because that's what we're interested in. That's what we're studying. And I'll bring this over so you can see it. I'm going to add down here at the bottom, I'm going to display the equation on the chart. First of all, I'm going to use a linear. There are other kinds of regressions in addition to linear regression, but we're not going to get into that excuse me, this semester. But the other thing I want to do is display the equation on the chart, and I want to display the R-squared value on the chart. And we'll be talking about these as we go through this chapter. So let's close that and see what we get. And there, in fact, is our equation. Y equals 5.7x plus 48. Those are the beta 1 and the beta 2 values, beta 0 values, as we know. And the R squared is a measure of the goodness of the fit. And you can see that the trend line here correlates quite well with the dots on the chart. The distance between each dot and the line on the chart is quite small, and that gives us an R squared value that says about 88% of the variation we see in these data can be explained by the regression line. Okay, that's great. What we're asked to do more specifically, using the formulas, we can verify that the values are what they are. What do these mean? Well, let's talk about that. What this means is that the R1 value, first of all, 5.7, says that for every 100 square feet of house size, we can expect a increase in the price of about $5,700. Now remember, when we're plotting house size here, this is in hundreds of feet, so 10 would correspond to a 1,000 square foot home, 25 would correspond to a 2,500 foot home. And the prices similarly are in thousands of dollars. So 100 is 100,000. So 5.7 for every unit increase in X, that is every 100 square feet increase in X, increases the price of the home by about $5.7 thousand. The beta zero value is an interesting one, 48. It says if we extend this line right on out with a ruler, it would cross the y-axis at about 48. That says that a house with 0 square feet, that is zero house, would have a value of about $48,000. Well, does that make sense? Not really, but maybe that's the value of the land underneath the house, and that might then make sense. Now, there are other factors that go into this, of course, so that's why the regression fit isn't exact. It's also why maybe that y-intercept value is off. In fact, as I mentioned a moment ago, maybe this line goes nonlinear as the size of the house decreases. It looks pretty linear in this range, but we can't be real sure. We couldn't use it to predict a 200 square foot house. First of all, that doesn't make much sense. Second of all, we don't know what the line how the line might curve as we got further on down here. Same way going up. Maybe luxury homes go up like this with a curve. But for the range of data we have, we can be pretty confident that those two values are what they seem to be. Now it asks us, what's the value of what would we predict the value of a 2,000 square foot home would be? So there's that's 2,000, but I'm going to say 2,000 square feet would have a price value. We can type the equation of 5.7. I'm not going to bother with all those extra digits. 5.7 times our 20 plus 48. So we could say that a 2,000 square foot home would have a value of about $162,000. And because I used the 20 in the formula here, we could put in 25 and see that it goes up to $190,500. Okay, that's enough for this. Let's move on now to problem, what's my next one here, 16 on page 517 in the book. It says, right when a least squares line is fit to the 10 observations, we obtain SSE equals 896.8. Let me put that in here. Get this back to 20. SSE equals 896.8. What's that mean? And it asked us to calculate S squared and S, and what are they all about? Well, the line that this equation that we've drawn here, y equals 5.7x plus 48, really has another term to it, an epsilon term, the error term, which tells us that, well, and we can expect that there's going to be an error term because we already know that only 88% of the variation is explained by the regression line. What this is saying is that for any particular size of home, 15, 20, you pick it, 20 let's say, we get the estimated value of 162, but the value is going to vary around that $162,000. Some are going to be higher, some are going to be lower. We're going to have a standard deviation. In fact, we can predict that if we use the t-statistic, we can use the t-table to calculate a confidence interval and a range. Right now, all we're asked to do is calculate S squared and S, the standard deviation, or really the mean square error, as it's called, and the point estimate. I mean the standard error of the point estimate. Okay, so looking on page 516, we know that SSE equals, S squared equals SSE, which is this value right here, divided by n minus 2. And we know that n is 10. There's 10 samples, so that n minus 2 is 8. We have 2 degrees of freedom, 8 degrees of freedom apparently. So that says S squared is 112.1, and S is therefore the square root of that value, or 10.58. So that says if we were to look at 2 standard deviations either side of the mean value of 162, roughly, just ballpark, give or take maybe 21 either side. So we would expect the confidence interval to 95% to be 41 to 83. We'll see how that stacks up when we get a little further along. But for now, that's a pretty good rough estimate. Okay, let's stop and I'll start another segment.